what's going on, chemistry students? I'm going to start up this class. I'm just going to show you guys the theory. I'm going to talk to you guys about how to do the lab that we're going to do, and then I want you guys to go and figure it out. Okay? So today's going to be a short web conference thing, and then I'm going to close it and cancel it. So that way we can do this, and you guys can actually do this when at home. I told you that at some point in time we were going to make bombs. You guys are all excited, and then sadly to say, you guys found out that what I meant to say was a bomb calorimeter. And you want to know what a bomb calorimeter is? It's 2 styrofoam cups. That's what it is. Ha ha. And I made a lid that is out of styrofoam plates. So Bradley, if you need to go and get styrofoam cups, go to a coffee store and ask them for styrofoam cups. Although I don't think you can ask Starbucks because they won't have it. If you have a Hydro Flask or anything similar, that would make a perfect calorimeter. That would actually be even better than these styrofoam cups. These ones are just way cheaper. You just have to make some kind of lid that can have a hole in it. So, yeah, if you have a Hydro Flask, get your Hydro Flask and use that. You don't need the styrofoam cups. You just need to make some kind of lid out of I don't know, styrofoam plates and put a hole in it. You also need a thermometer. You're going to need to get one of those. Okay? All right. You need a thermometer. That's a key to this experiment. So, let me tell you what I've been going over in class. On Monday, we covered this thing. That was actually really. Andre told me that the analogy that I had on Monday was the best one. Oh no, Tejas. Tejas told me that the analogy that I had on Monday was the best one I've ever had, which is basically saying that all the other ones sucked. Right? Yeah. Okay.
I didn't say that.
Well, that's what it sounded like to me. Nah, I'm kidding. The analogy that I came up with was one of the best ones. So if you have a chance, watch the video. I posted it up to the class. Please check out the archive from Monday. I thought it was pretty good. Let me cover, we covered 2 equations, and I'll tell you what they are. And they're not even hard to memorize. It's Q equals MCAT, and Q equals ML. Got it? And we talked about phase changes of matter. We talked about water, what ends up happening, and I was thinking about doing this experiment with you today, but literally I thought about it and I was like, I'm going to do a demonstration to have my students watch water boil. I think that would be a little boring. But anyway, imagine if I had an ice cube that was really low temperature, like let's say negative 20 degrees Celsius ice. So it's colder than just the freezing point of water. I had it in the freezer for a very long time. Okay? This is the graph of your temperature, and then this will be the graph of my Q, the energy that I add into this thing. Are we cool with that? So over here, let's say it starts off at negative 20 degrees Celsius. There's some important temperatures that have to do with water. What's one of the other important temperatures? Why is that one important with water? Please tell me, what's 0 degrees Celsius?
0 degrees Celsius is absolute zero.
No, it's not absolute zero. It's 273 degrees Kelvin. 0 degrees Kelvin is absolute zero. But it's freezing point of water, right? That's an important number. Cool? All right. And what's another important number up here? What? 100. 100 degrees Celsius. Why is that?
370.
That's the boiling point. It's 300 something blah 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 Fahrenheit. But when we're talking about Celsius, remember Celsius is the one that makes sense. Fahrenheit doesn't make any sense. So Celsius is like, oh yeah, 0 degrees Celsius, that would make perfect sense. 100 degrees Celsius, that makes perfect sense as to why I would do that, right? All right. The Fahrenheit, that's the one where this is the same as 32, and this is the same as 370 something stupid. I don't know. I don't even know it off the top of my head. That's how dumb it is. So we're dealing with Celsius. Do you guys understand what's going on here? Now, as I add energy to my block of ice that is at negative 20 degrees Celsius, what's going to happen as I slowly add energy as I go along the side?
It's going to increase.
The temperature is going to increase. Got it? Now here's the interesting part. As I add energy to this thing, once the thing reaches 0 degrees Celsius, what happens? Does it just go right past there? No. What happens is actually, it goes like this. As you add more and more energy, the temperature won't change. Why is that? Well, because water can exist at 0 degrees in two different forms. It can exist as solid water and liquid water, right? Well, not exactly at 0 degrees liquid water. You'll have like liquid water at 0.000001. But it can exist close to 0 in two different forms. This horizontal line is representing changing all of the solid ice into liquid water. You're putting in energy, but it's not changing the temperature. All it's doing is it's changing the form from liquid to solid, or solid to liquid. Does that make sense? All right. And then once you've turned all of your liquid water or your solid water into liquid water, you keep adding energy, and what's going to happen? You're going to go up again. We cool? And then what's going to happen at 100 degrees? It's going to start to boil, right? But if you leave your thermometer inside of a boiling pot of water, does your boiling pot of water get hotter and hotter and hotter? No. You try this next time you boil a pot of water. If you boil a pot of water, you just leave it on the stove. The temperature won't go above 100 degrees Celsius. It will stay at 100 degrees Celsius.
You have to add more energy in order to get it.
No, well, you're adding energy. More and more energy.
You have to add stronger amount.
You're adding stronger amount of energy. It
Well,
won't
it turns
change the
into steam.
temperature. 100 degrees Celsius. Same.
That's it. You can't go beyond that.
You can. But before you go beyond 100 degrees Celsius, you have to do what? You have
Steam.
You have to turn all of that liquid into a gas. And then the gas can go above 100 degrees Celsius. Once every last drop of that water went from a solid or from a liquid to a gas. Before that, all that energy is just converting liquid water into steam. All that energy is just going straight into there. Don't you guys remember? This is the second toll booth. You don't get to pass this thing until you pay off everything. All 2,200 or 2,300 and whatever dollars. I forgot what the number was. Does that make sense? And the way I describe this, I'll tell you the analogy because you missed Monday's lecture, which is kind of a bummer because I thought it was a good one. But basically, there's two equations. Or the analogy I had was, actually, you know what? I don't want to ruin it. I want you guys to watch the video because I thought it was good. I thought it was a really good lesson. So here, that's the whole gist of things. But today, we're not going to cover any phase changes whatsoever. We're only going to stick with moving between one temperature to another temperature. This equation you use when you have phase changes. So, we're not going to be doing this thing. All we're going to be doing is this thing. Q equals mc delta T. What does M stand for?
Mass.
Mass. Good. So the amount of energy it takes for me to move from one temperature to another depends on how much of the stuff I have. Does that make sense?
Yeah.
Perfect. I understand why mass is there. Okay. What about delta T? What is that?
Change in temperature.
Change in temperature. So the amount of energy I need to add depends on how different you want that temperature to be. Is that true? Sure, that makes sense. All right, here's where the tricky part gets in. What is the C? C is called a specific heat capacity.
Did anyone take physical science last year?
I took it like 2 years ago.
Do you guys recall seeing specific heat capacity before? All right. What this is it's kind of a measurement of an object's ability to absorb energy. For example, I'll tell you a good example. If you, all right, say that you have 2 pots on a stove, okay? And you fill up one pot with water, and you fill up one pot with nothing. So you have a pot of water on the stove, and you have an empty pot. And you leave it on for 10 seconds on the highest setting, both of them on burners, okay? Which would you rather? Put your hand in the one that has water in it? Just 10 seconds. It's only been on the burner for 10 seconds. Put your hand in the one that has water on it, or put your hand straight in the pot that doesn't have any water.
Water.
Why?
Because there's more to heat up, so it takes a longer amount of time.
Okay. Well, which one absorbs heat faster?
The metal pan.
The metal pan. It absorbs the heat real quick, and then burns you very quick too. Does that make sense? So your C will actually be really small for the metal pan, whereas your C for water will be kind of a big number. Does that make sense? C is kind of like a measurement of how easy something absorbs energy. Yeah, good. All right. So, what is the C for water? The C for water was 4.18 joules per 4.18 joules per. Shoot, I forgot what the units of water is. Is it? Well, I can figure it out. It's joules per gram Kelvin. It's got to be that, right? Actually, it's joules per gram Celsius. Because if I solve for C, I'll get Q over MT, right? And Q is joules, M is grams, and T is Kelvin, or Celsius. We cool with that? In a different units, I can say if there's 2 ways to measure energy. One way is to measure it in joules. Another way is to measure it is in calories, which is probably something you're familiar with, right? So C in calories is actually 1 calorie for every gram Celsius. In fact, that is how we define a calorie. A calorie is how much energy it takes to move 1 gram of water 1 degree. So what is the actual definition of a calorie? Well, it's however much energy it takes to move 1 gram of water 1 full degree. That's it. We cool with that?
Yep.
All right. So check this out. Here's what's going to happen. Here's our lab that we're going to do today. I'm going to take a piece of metal, and I think these are steel ball bearings. I don't
Not
know.
hot?
Oh, no, they're not hot yet.
Oh. I was like, are you like Superman?
I'm gonna take a piece of metal.
Because I thought I saw it smoking earlier. I was like, holy crap.
Yeah, I know. He's bad to the bone. All right, I'm gonna take a piece of metal. I think they are steel. I'm not sure. I think they're stainless steel, but to be honest with you, I don't know.
Oh, it's lead roll screw.
No. I mean, could be.
Mercury.
Well, it wouldn't be in that form if it were mercury.
I know. It'd be
But
that way. I know.
I think those are steel, stainless steel, but they could be, a different mixture of different things. But I'm pretty sure that they're steel. But anyway, what I want to do is I'm going to figure out the specific heat capacity of that, and we're going to assume that is that going to have a high specific heat capacity or a small one?
High.
Small,
It's gonna get hot faster.
because it gets hot faster.
Um,
Right? If it has a big one, then it's kind of like rubber, right? Rubber doesn't get hot very fast. So, and water is 1, so this one's probably going to be a decimal, like point, whatever. Are we cool with that? I want to figure out exactly what that heat capacity is. So, here's what I do. I'm going to take a cup, and in our case, we have a styrofoam cup. I'm going to fill it up with water. I'm going to know exactly how much water I have. In this lab, measurements are key. All right? I'm going to take a steel ball bearing, and I'm going to heat it until it gets really hot. I'm going to measure the mass of this steel ball bearing. So I have my mass of ball bearing, and I have my, we'll call it MS, or mass of steel, or whatever it is. And I'll call this one MW, for my mass of water.
Instead of massive steel.
Sure, massive steel. Got it. I'm going to heat it up. So I'm going to have a temperature initial of T initial of steel. I'm putting a bunch of subscripts on there. I'm just trying to make it so I can keep my variables all the same. I'm also going to have a temperature initial of water. Got it? Then what I'm going to do is I'm going to drop the ball bearing into the cup. So here's scenario 1, here's scenario 2. If I wait long enough, what's going to happen to the water?
increase in heat.
It will increase, right? And what's going to happen to the temperature of the ball bearing?
Decrease.
It will decrease. This guy will lose energy and the water will gain energy. We're cool with that? In fact, I would almost venture to say that I could measure exactly how much energy this ball bearing lost if I can know exactly how much this water gained, right? How much energy that water gained. If I could measure how much energy, the Q, that the water gained, then I can tell you the Q that the ball bearing lost. Assuming, of course, that all that energy exchange happens between just the water and the ball bearing, and I don't have energy being lost out of my the sides of my calorimeter. Does that make sense? Which is why we don't do this experiment without a cover. We put a cover on it, and not only that, I actually want you to put tape around this thing to get a nice good seal on that. If you want, you can even use Play-Doh and stick the Play-Doh in the seams over there. And when you put the thermometer in, because why would we use a thermometer? Well, you would use the thermometer so you can measure. You're not going to measure Q. I don't have any instrument that will measure Q. But I do have a thermometer that will measure delta T. And you know the M and you know the C of water. You can figure out the Q of the water. Does that make sense? So this guy gains this much, he gains this much energy. This would be mass of water. This would be C of water. This would be the delta T of water. Got it? If I wait eventually, what can you definitely tell me about the temperature of the ball bearing and the temperature of the water. Come on, you guys.
Wait, you do what?
Sorry.
What can you tell me about what will happen eventually to the temperature of the ball bearing and the water?
Like a seesaw.
What?
Like a seesaw.
They're going to seesaw?
Except not evenly. The water will.
Well, the water temperature will go up, and the metal ball will go down, the temperature. But is it going to end up being where
No.
what's going to happen?
They're gonna be equal.
They're going to be equal, right?
Yeah.
They're going to meet at some point in the middle. So my T final in my delta T, by the way, delta T means T final minus T initial, right?
Yeah.
So my T final for both cases is going to be the same. Does that make sense? So what I'm going to do, if this is my Q for my water, and my Q for my steel is mass of steel, C of steel, delta T of steel, then I can say that this is equal to that, right? Actually, I'm thinking, do I say that this is equal to the negative of this? Yeah, I think I do. QS is equal to negative QW. Because the amount of energy this guy gains is the amount of energy this guy loses. So they're equal. They're almost equal to each other. They're opposite equal. Does that make sense? So then when I set those equal to each other, I know the mass, I know my temperatures, I know my mass of water, I know my C of water, I know my delta T my delta T of water. I only have the CS to solve for it. So you can actually identify what the specific heat is of a metal by just using a styrofoam cup and a thermometer and, whatever. We're cool? Any questions?
Cherry cuts.
So I didn't even solve any problems for you because I feel like I want you to do the lab and then I'll show you guys how to do some example problems.
Can you leave that there?
I'll leave it here. And I even have a write-up for you on how to do this. I'll try to post this for you guys, Bradley. But anyway, I'm going to stop class and I'm going to heat up some metal ball bearings, and I gave you guys vague enough directions to be able to solve this thing. I would recommend, I don't think we even have enough steel stands, like stands. So I'm going to try to do this, I'm going to do this experiment too, and we'll see if we can do, figure out what the C of the ball bearing is. Got it? All right, cool. If you don't have any questions, I'm going to stop this and I'm going to just let you guys at it. All right, let's go for it. Can you